All right, we're going to look at paleomagnetism. We're going to be able to identify how Earth's magnetic field changes. Right? We've talked about this dynamo effect that generates this magnetic field. And we're going to actually look at how it's recorded in oceanic crust. We can actually study the Earth's magnetic field at how it's oscillated or flipped polarity. So we do this by studying the oceanic crust, and we can look at divergent boundaries. Here we find that what's in red, if I give you a little summary here, what's in red is the youngest oceanic crust. And this here happens to be the Mid-Atlantic Ridge. We're looking at the United States and North America here. Here we've got South America. Here we have Africa, and here we have Europe. And if you look at what's dividing the kind of the geographic midpoint between North America and Europe, and even into North Africa, you see this color code. You see this red and orange into yellows, greens, and blues. You see this color, and it's essentially saying that if we rewind time, that Africa, Europe, and North America come back together. And this is consistent with the concept of Pangea, that the age of the ocean floor, right, oceanic crust is igneous rock, thus we can radiometrically date it to find its age, further supports the theory of plate tectonics. And when, as simple as that sounds, we can really use this concept of paleomagnetism, that Earth's magnetic field changes, it reverses infrequently over time. And currently the Earth's magnetic field is a location that we call normal. In other words, we would say that the magnetic needle north points to where we think of as geographic north, and the south end of the compass points to what we call geographic south. And here are magnetic field lines that they're coming out of the South Pole, because the Earth's interior, the dynamo effect is generating the magnetic field, that these field lines are surrounding space that generates this magnetic field. And as a result of that, mafic oceanic crust, it's got these iron minerals within it, we would say that they orient themselves based on the magnetic field. And when it reverses, we call this reverse polarity. And this has happened thousands of times in Earth's history, and it's very well documented in Earth's oceanic crust. So oceanic crust is igneous, therefore radiometric dating, and the mafic minerals contain iron, so the iron act as little compasses in here. So if I look at letter A, it shows the Earth resembles a bar magnet. Letter B shows the magnetic field lines, that any object inside the magnetic field, that has magnetic properties such as iron, aligns itself. And then letter C, here we can say that oceanic crust, basalt, records the changes in the Earth's magnetic field as it goes from being a liquid to a solid and solidifies into solid rock. So here's an example that we can get from our textbook, and this would be an ocean ridge. This would be the ridge axis. So we can say it's the Mid-Atlantic Ridge or any general or average ridge, but I want to pay attention to the symmetry. That if we pay attention to what's happening on this side, it's symmetrical to what's taking place on this side. Just like this picture right here is symmetrical, we would say this is the crest of the ridge, that this side is symmetrical to this side. Well, this is the same concept, it's just a little different depiction. That over time, this divergent boundary spreads this way, and this half spreads this way. And that the greater the amount of time, we could say that the red coloration would be normal polarity, and we would say that the white is reverse. So we go normal, reverse, normal. In this picture, it's completely normal. Oh, excuse me, I didn't read the signs here. Period of normal magnetism is in white, and the pink is reverse, so my bad. Here's a period of reverse magnetism. You say, well, how do I know? Well, this pink is what's the youngest, so this would be the key for that. So I've got reverse, pink, white is normal, and this right here would be reverse. And it's symmetrical to the other side. So I would go reverse, normal, and then here would be my ridge system. And this is studied when we study the ocean floor using a magnetometer. So we look at the symmetry here that helps tell the story. So if we were to kind of use the concept of polar wandering here, polar wandering is simply the concept of viewing these plotted positions of the North Pole with respect to Europe. This picture shows that the pole had gradually wandered from a location to its present location. And this was strong evidence that either the poles had migrated through time or that the rock moved. And Europe and North America had drifted in relation to the poles. So what we're looking at is the apparent wandering path for Eurasia and the apparent polar wandering path for North America. And essentially what it's saying is that if we were to rewind time and we were to go back to this supercontinent, we would say that they align very nicely, and we could say very confidently the plates have moved, and this is actually nicely embedded in the rock that we can tell the story. So when I align these together, they pretty well line up, and it's simply saying that it's the continents that moved, not necessarily the pole.